Section 3.2, Solving Linear Systems Algebraically. So we've solved linear systems graphically, finding that point of intersection. Now we're going to solve them algebraically. So sometimes it's hard to determine the exact point of intersection of two lines when we try to solve the system graphically. And to illustrate that, I'd like you to pause the video and go ahead and try to graph both of these lines. So I graphed the first line carefully in red, plotting every point I can in the coordinate plane given. And then I plotted every point that I could for the second line in green. And you'll notice that we can't find definitively what that point of intersection is. We can estimate, but we can't find exactly what the point of intersection is. And so this is one reason that we're going to learn two methods to solve systems algebraically. So one of the ways that we can do that is using the substitution method. And so the first step in the substitution method is to solve one of the equations for one of its variables. So typically your equations are going to be in x and y, so you would have to solve one of them for either x or y. After you do that, you would substitute the expression that you found from step 1 into the other equation and solve for the variable that's left in that equation. And finally, after you found the value for one variable, you're going to substitute it into one of the original equations to find the other variable. This sounds a lot more difficult than it really is, so let's go ahead and do an example. So this first example, 2x plus 3y equals 1 and x minus 2y equals 4. Well, if we solve for either x or y in the first equation, we're going to end up needing to divide, and we are probably going to end up with some fractions. But if you look at the second equation, the x already has a coefficient of 1. So if we go ahead and solve for x in that equation, we get x equals 2y plus 4. And so now we're going to take that and substitute that in for x into the other equation. So my other equation is 2x plus 3y equals 1. And so I'm still going to have 2x, but in place of the x, I put what it's equal to, which is 2y plus 4. The rest of the equation remains the same. And now I have one equation with y, so I can go ahead and solve that equation for y. So if you want to go ahead and pause the video and finish doing this, and then come back to see if we get the same answer. So 7y plus 8 equals 1. Continuing to solve this equation, we get that y equals negative 1. And now we can take this back and substitute it into either one of the original equations. In fact, this x equals 2y plus 4 is a rewritten form of the original equation. So when we plug negative 1 in, we can see that x equals 2. So you need to write your solution as an ordered pair. Of course, the x-coordinate first and then the y-coordinate, so 2, negative 1. We can check our solution. If we plug 2, negative 1 into the original equation, we can see that it works. And we have to also plug it into the second equation, because for it to be a point of intersection, it's got to lie on both those lines, and so it does indeed work. The second method is called linear combination, or it's also called elimination. And the steps to that would be that the first thing you need to do is multiply one or possibly both of the equations by a constant so that one of the variables has the same but opposite coefficients, remembering that coefficients are the numbers in front of the variables. Then you're going to add those revised equations from step 1, and when you're adding the like terms, this will eliminate one of the variables, and there's the name elimination. And then we're going to solve for the remaining variable. And then, like substitution, after you find the value for one of the variables, you can go back to one of the original equations to determine the value of the other variable. So let's go ahead and do an example of this method. So we have 8x plus 2y equals 4, and 2x minus 3y equals negative 13. So we need to get it so one of the variables has the same but opposite coefficient. Well, since 2 divides evenly into 8, I'm going to choose to multiply the second equation, everything in it, by negative 4. So rewriting my first equation, 8x plus 2y equals 4, and multiplying the second equation by negative 4, I get negative 8x plus 12y equals a positive 52. And so now I'm going to go ahead and add these equations together, and you can see that my x's eliminate. 8x minus 8x is 0. Adding my y's, I get 14y, and adding my constants, I get that it equals 56. So now simply solving this, I get y equals 4. And so now I'm going to go back to one of my original equations. It doesn't matter which one you use. I'm choosing to use the first one. So I'm going to plug the 4 in for y. So 8x plus 2 times 4 equals 4. And now I can go ahead and solve this equation for x. And you see that x equals negative 1/2. Again, you need to make sure that you write your answer, your solution, as a set of ordered pairs, because this is the point that lies on both of those lines. And again, we can check our solution. Plugging it into the first order, or the first equation, I see that it does indeed work. And plugging negative 1/2 4 into the second equation, I see that that one also works. So negative 1/2 4 is indeed the solution. So now we have a few examples to just kind of look at them and determine which method we should use. And so with this example, 2x minus 3y equals 4 and 6x minus 9y equals 8, since none of those variables have a coefficient of 1, we're probably going to end up with fractions, and you probably don't like to deal with fractions any more than I do. So let's look at what we could multiply one of the equations by. Well, what comes to me immediately is that if we were to multiply the first equation by negative 3, then my x's would have the same but opposite coefficient. So when we multiply the top equation, we get negative 6x plus 9y equals negative 12. Make sure you multiply everything. And rewriting the second equation, and now again adding these together, except this time my x's disappear, eliminate, and my y's disappear, so I get 0 equals negative 4. Well, this obviously isn't true. So since there is no it's not true, there is no solution. So these lines would be parallel. In this next example, well, since my x has a coefficient of 1, well, my y has a coefficient of negative 1, so that would be fairly simple also. But let's go ahead and try to solve this one by substitution. So let's solve the first equation for x, adding y to both sides. I get x equals y plus 4. And now we're going to substitute y plus 4 in for x in the other equation. So negative 6 in place of x, we're going to put y plus 4, plus 6y equals negative 24. And now we have an equation with just y, so go ahead and distribute and solve for y. When we distribute, we get negative 6y minus 24 plus 6y equals negative 24. So my y's cancel each other out, and I end up with negative 24 equals negative 24. Well, since this is true, that means there are infinitely many solutions. You can't say all real numbers, but you can say infinitely many solutions. Okay, let's try to do an example that has a solution now. So if we look at this example, again, we don't probably want to use substitution because we would end up with fractions if we solved one of those equations for either x or y. So let's go ahead and use elimination or linear combination. So if we multiply the top equation by a positive 6, we would get that our y's are the same but opposite. And so when we add both equations together, 75x equals 122, we get x equals 122 over 75. I don't know what decimal that is, but whether it's a decimal or a fraction, it's a rather nasty term to substitute back into the other one. So I think in this case what might be easier is let's just use linear combination again. So rewriting the the second equation, but let's multiply it by negative 4 because then my x's will eliminate. I will get 12x and negative 12x. Bringing down the other equation, the top equation, 12x minus 2y equals 21. And now when I add these together, my x's eliminate, and I get another nasty fraction for the y. So again, making sure that you remember to write them as an ordered pair. I will save us all the agony of substituting that in and checking that solution. I have done that, and it is a solution. If you'd like to go ahead and try, then I would encourage you to do so. And now I'd like you to write this problem down. on your note packet. It's not in your note packet. 1/2 x plus 2/3 y equals 5/6, and 5/12 x plus 7/12 y equals 3/4. Now, a lot of you might find this intimidating because of the fractions, but let's go ahead and get rid of the fractions. If our top equation has denominators of 2, 3, and 6, what would be the least common denominator? Well, hopefully you realize and remember that 6 would be the least common denominator, so if we multiply that top equation, everything, by 6, then we get rid of the fractions. We end up with 3x plus 4y equals 5. So again, the denominators in my second equation, 12, 12, and 4, the least common denominator would be 12, so if we multiply everything by 12, again, we get rid of those denominators, and now we have a very reasonable problem to deal with. Again, what occurs to me, you could look at this different ways, but to me, I'm going to eliminate the x's, and so in order to do that, I'm going to multiply the top equation by 5, negative 5, and the bottom equation by 3. When I do that, I get negative 15x minus 20y equals negative 25, and positive 15x plus 21y equals 27. And when I add these together and solve, I get that 1y, or y, equals 2. If I go ahead and plug that in to either one of my original equations, modified original equations are making it easier, I get that x equals negative 1. So my solution is negative 1, 2. And I went ahead and checked this, and you can see that it does work. And finally, the dreaded word problem. At a pizza restaurant, it costs $4 to make a small pizza that sells for $12, and it costs $6 to make a large pizza that sells for $15. In 1 week, a restaurant spent a total of $1,100 making pizzas and sold all of them for $2,910. How many small pizzas were made or sold? The first thing we need to do is define our variable, and the place you look to define your variable is always in the question, and it asks how many small pizzas. Therefore, x is going to be the number of small pizzas, and the only other thing we're talking about is large pizzas. So now let's organize our information. We're making and selling pizzas. So what numbers go under the column of making pizzas, and what column numbers go under selling? Well, the first sentence says that it costs $4 to make a small pizza and $12 to sell one. $6 to make a large pizza, and they sell it for $15. And finally, they have spent a total of $1,100 making the pizzas, and from selling them, they brought in $2,910. And so to some extent, your equations should fall right into place. Remember, we're using our old model of number times the price. So we have $4 times the number of small pizzas plus $6 times the number of large pizzas equals $1,100. That's the equation for making our pizzas. $12 times the number of small, plus 15 times the number of large equals 2,910. And now I encourage you to pause the video and go ahead and solve this. And the reason I solved it for x was because the question only asks, in this particular case, how many small pizzas were made and sold. Since I defined my x as the number of small pizzas, it made sense to solve it for the x. And I find that there are 80 small pizzas. Make sure you're answering the question. If you have any questions, please make sure you bring them to class. And as usual, please make sure you go back and do the notes check.